started. Thanks everybody for joining us today. We're really excited to bring you another scientific computing webinar from our ongoing series. These two webinars, or the past webinar we did and this one, are both on AWS ParallelCluster, which is an HPC toolkit for AWS. And the previous webinar was on more general interest topics, so ParallelCluster tips, tricks, and lessons learned. The webinar today is going to be a much more niche topic, really focusing on a specific scientific use case, particularly computational chemistry. And computational chemistry often uses commercial applications. So the Schrödinger suite is the one we're going to kind of go deeper on today. And so how can you use ParallelCluster to do license-aware scheduling with Schrödinger? So just as a sort of a few announcements, this video will be released on Friday. So anyone who registered for the webinar today will get a copy of that video, and we'll release it along with the slides by Friday. And so, yeah, without further ado, today's presenter once again is Chris Dagdigian. He's one of the co-founders of BioTeam. He's one of our senior technical directors of infrastructure. And for over 20 years, he's been designing and building HPC for research. And he's also a major supporter of open source and life sciences research in general. So Chris,
all right,
take it away.
Thanks a lot, Adam. Hi, everybody. I actually have to acknowledge my hosts at TAC, the Texas Advanced Computing Center out in Austin. This is the first time I've done a webinar while out on the road, but because I am abusing their guest Wi-Fi, I am actually going to turn off my camera. The idea being is that we want to give precedence to the audio and the video. So going to wave and thank you for showing up here, and I'm just about to go dark. All right, with that said, I'm going to skip the basic introduction about myself. I think that the main thing to get across is, just like last week's or the last webinar, is this isn't intended to be a sort of really slick, overly engineered presentation. We're trying to sort of get personal. We're trying to provide sort of actionable advices. This is a long-winded way of saying it's kind of a boring and dry deck, and any mistakes in the presentation are my own. The goal is not to wow you with anything fancy. The goal is to sort of deliver practical information that hopefully you'll find useful down the road. The slides are very word heavy. That's just because historically we found that our slide decks have a lifespan well beyond the event. They get passed around, they get stored in various locations. So we try to put as much text into the slides as we can because they can serve as kind of living reference material or a how-to document down the road. So again, as Adam alluded to, I'm sort of nervous about the content of this material because this is a really super niche topic. So I want to make sure that the people who are attending here don't have their time wasted. So I want to sort of quickly review the intended audience for this type of talk. If you're an existing AWS user or your AWS cloud user who also is using or is interested in the full suite of the Schrödinger platform, which actually covers, I call them a comp chem tool, but yeah, they cover a much broader set of industry needs, ranging small molecule biologic drug discovery all the way down to material science. So the specific audience intended here is Schrödinger is commercially licensed. The features and the applications don't launch unless they can check out a license. So the purpose of this webinar is really to show you how to imbue license-aware job scheduling into AWS ParallelCluster so that you can run your licensed jobs from the Schrödinger platform on auto-scaling HPC clusters in AWS. And then finally, there might be another sub-audience type here where if you're just generally interested in how to make Slurm license aware, in particular, if you want to understand how most people take FlexLM license servers and make them report into Slurm, then the material in this deck, barring the specific Schrödinger customizations, would generally be of interest for you. The reason for this talk is that in our world, in our world of data intensive life science, Schrödinger is dominant. It's one of the top 2 or 3 sort of tooling stacks that we deal with in this particular realm of science. But the interesting thing is Schrödinger itself, the platform, is really complicated and really powerful. In particular, it ships with its own internal job control, job submission, monitoring, and management stack. So it knows how to send work to remote systems, whether they be standalone, but it also knows how to submit jobs to common job grid schedulers. So the native job control daemon in the Schrödinger suite knows how to talk to Slurm, it knows how to talk to PBS, it knows how to talk to grid engines. So from a technical and sort of usability and integration viewpoint, it's actually a really interesting project to work with, or a platform to work on. But finally, the thing that makes it extra special to deal with is that it flat out doesn't work unless there's a license server in the mix and the applications can check out features and entitlements. So we have this additional technical requirement of making sure that jobs only run when there is a license-free Otherwise, the job is just going to die. It's going to die with a license not found or a license not available error. The other reason why we put this sort of niche talk together is I sort of gauge when to do technical writing or technical speaking based on how many customers ask me to do the same thing. And license-aware job scheduling for Schrödinger on ParallelCluster is something that I've done at least 4 times this year and maybe half a dozen times. So it's happened often enough that I think there might be at least a slightly broader audience interest in this topic. So the goal for today is really just to cover step by step in a really dry, super boring way, but just want to go step by step the process of making it work. The reason why is this was a long learning process for me. The documentation for doing this is scattered in a bunch of different places. I made some mistakes. I have some lessons learned. So we really kind of wanted to, my goal is if I can sort of centralize this into sort of an easy to follow how to, that's the ideal takeaway for people who attend this webinar. And then finally, because ParallelCluster is a flexible beast, we are specifically talking about ParallelCluster with the Slurm batch scheduler. We're specifically talking about making Slurm license aware. So if you run ParallelCluster with AWS batch under the hood, this material is not going to be for you. So if you're listening to me now and you're turned off and you already haven't quit, what I would recommend to do is that we did a much broader, much more sort of wide spanning webinar a few weeks ago on general best practices, lessons learned, and everything that we've sort of internally recognized at BioTeam about how to effectively use and deploy ParallelCluster. So if you're interested in ParallelCluster in a more general sense, check out that short link at the end. The talk slides and video of that sort of broader webinar are available. I think you can tell I'm concerned about wasting people's time, so I just want to make sure you're in the right webinar and you're going to get something out of this. So I'm going to skip these slides. The bolus here is BioTeam originally made a mistake of assuming that everybody who engages with us or talks to us knows who we are and what we do. But it turns out people find us in different ways. Google keywords, they find our slide decks floating around on the internet. And it turns out that a bunch of people who find our materials or engage with us don't actually know who we are. But I don't want to put a long involved, sort of marketing pitch into this material, but on the assumption that these slide decks are going to live beyond this event. If you're interested in a broad sense of who BioTeam is and what we're capable of doing, we've got some slides that cover it. And if it interests you, reach out. We're easy to find. I'm Chris@bioteam.net. That is the end of any type of sales pitch that I'm going to do for you. So right now, we're a few minutes into the webinar. I've broken up this material into a couple of different sort of sections. And so the first section here is generally things to think about in advance before you even deploy a ParallelCluster environment. So we're not even at licensing or Slurm or anything else yet. So the stuff you want to think about ahead of time. My particular pet peeve is a lot of cloud marketing talks about auto-scaling HPC as completely disposable. You throw it away when you're done. But in the real world, my users are humans. They're not, automated workflow engines. There's a value of having some things that persist and stick around. And the number one persistent thing that we always recommend in this context is having a persistence POSIX storage layer. In this case, EFS from the AWS managed NFS service is great. But what we're talking about here is I may create and destroy clusters at will, but I can always mount an NFS share to them. And that NFS share has my user home directories, it has my scientific applications, it has my tools, it's got my environment module files, things like that. So really just want to make the case here that one of the things you should be thinking about is what infrastructure do you have that you want to persist if your HPC clusters on the cloud come and go all the time. For us, there's a huge value in having a persistent POSIX layer. And this is not just a ParallelCluster thing. If you do this right, this becomes the POSIX layer that gets mounted to every Linux system in your AWS-based scientific computing environment. It's just a good place to put your apps, tools, user home folders, things like that, Conda environments, whatnot. So the second thing that we want to talk about is you're going to want to design your storage layout, in particular because Schrödinger is kind of a big beast to install. It's always safe to assume, as within any commonly used scientific tool, you're always going to have to deal with multiple versions of the same tool installed on the same system at the same time. So this is a long-winded way of saying, think about your directory paths and think about your naming structure. And the whole point of the graphic on this slide is to show you how I like to organize Schrödinger. I like to do a base directory named Schrödinger, and then underneath I have a subdirectory that corresponds to the particular versioned release of Schrödinger. So that way, if I have a directory called Schrödinger, I can have 2022.3, 2021.-4, and multiple versions of Schrödinger all sort of installed under an easy to navigate file hierarchy and file path. The related comment to this is that if you buy my argument that you're always going to have multiple versions of the same tool installed in the system, you're probably going to need a way to manage it. And so I'm a big fan of environment modules. There's more modern and sort of cool stuff out there, but environment modules works for me. The whole purpose of this screenshot is if you look at the image on the top of the slide, you can see here there's a module set up for 2 different versions of the Schrödinger suite. And then the bottom image is showing you kind of an example more from the scientific computing world where we have 2 different versions and 4 different flavors of the NAMD molecular dynamics app. And this is not unusual. This is bog standard normal stuff in data intensive life science computing. So, you know, in terms of other considerations beyond EFS, you want to think about how you're going to manage software installations, how you're going to present them to your systems, and in particular, how are you going to deal with multiple versions of the same file. The second thing I want to talk about when it has come down to networking and security groups, ParallelCluster makes it easy to add a list of security group IDs or security groups. And I would recommend carving out and persisting a security group that's specific to Schrödinger, and I'll talk about why in a little bit. There's certain port ranges that you might want to open up, and you generally would only want them on hosts that are running or servicing a Schrödinger stack. So ParallelCluster makes it easy if you want to have 1 or more security groups aligned with your infrastructure, piece of cake. This is the area about security groups, is that Schrödinger documentation really bluntly states that you want to open access to every port above 1024. That's the type of language that really freaks out InfoSec people. They don't like opening wide port ranges for things like that. So my recommendation is if you're just starting out and you have to have the conversation, push forward with a trial or a pilot that does open up the ranges above 1024. Your life is going to be easier. The job control stuff is going to work. However, Schrödinger support is fantastic. Their documentation is great. If you're in an InfoSec environment where you have to constrain the port ranges involved, you can do it via environment variables. So you'll just have to start, you'll have to get prepared to manage some JProxy and JServer port variables if you want to constrain the networking range that Schrödinger's job control system uses to submit work to a cluster and monitor the process of that job through its life cycle. The second thing I want to mention here is that you know, anybody who's been using Schrödinger for a long time is very familiar with job control. Schrödinger is in the midst of pushing out a complete replacement for job control. They call it JobServer. If you're using a relatively new version or modern version of Schrödinger, that's actually available to you right now. It's disabled by default, but it's activated via feature flag. The reason why I'm putting this into this talk is that at some point, all of this information about job control is going to become obsolete because the Schrödinger folks will have switched over to the JobServer framework. There are significant advantages to JobServer. It's sort of out of scope for this talk, but the big one for me relative to the security group conversation is you only need to open up 2 TCP ports. So even just from an InfoSec perspective, there's some sort of configuration advantages to activating and using the JobServer framework. So again, just setting the stage here, everything I talk about job control might become obsolete when Schrödinger sort of moves the JobServer functionality into production. We'll have to redo the documentation and the webinar for that. Finally, this is a relatively recent limitation is if you want to activate license-aware job scheduling in Slurm, you must have accounting set up. Accounting is not something that ships by default activated in AWS ParallelCluster, although given the rate of improvements in the ParallelCluster product, it wouldn't be surprised me if accounting is activated relatively soon in some of their upcoming releases or feature roadmap. The problem is that older versions of Slurm made it really easy to set up accounting because older versions of Slurm allowed you just to dump your accounting data to a text file. So it was a simple 2-line config. It was really easy to activate accounting with Slurm. However, starting in ParallelCluster release 3. something, they upgraded the version of Slurm that ships with ParallelCluster, and the new version of Slurm no longer supports sending accounting data to text files. This is a long-winded way of saying if you want to do license-aware job scheduling with Schrödinger, you're going to need an SQL database. You could definitely install MySQL on your head node. You could treat the sort of accounting database and the database as disposable, but I'm of the belief that there's value in persisting Slurm accounting data, particularly job data relating to commercial software assets that are fairly expensive to license. So our general recommendation is you'll probably want an SQL instance, you know, AWS RDS or dedicated that is separate, another sort of persistent system, just like EFS that does not live or die based on the life cycle of your compute node or your HPC cluster. Finally, I'm not going to talk about this except to say whenever you find online documentation about creating databases or Stack Exchange posts, it always starts out with typing a command that says grant all or grant all privileges. That grant all stuff never works for me on Amazon because in RDS, there are certain grants that they flat out don't allow mere mortals to do. So I've done the work. If you're interested in a database creation command with grant commands that actually work, that will result in a functional Slurm accounting database. It's documented on this slide. If you find documentation online, like I said, the big thing that bites you with AWS RDS is, typically any documentation that says grant all is not going to work, and you've got to figure out the appropriate grant commands to make when you're doing it for real. So documented here in text and a screenshot if this has bitten anybody else. Finally, I can't stress this enough. ParallelCluster makes it super trivial to tag your stuff. It's 2022. Everybody should be tagging your stuff. And given that we're talking about not cheap, commercially licensed software, at some point, someone is probably going to want you to kick out a cost report or a spend report on the HPC resources that are servicing your Schrödinger environment. So if you are going to do tagging, you should absolutely do tagging with at least a couple of tags that are recognized as AWS cost allocation tags. So in the screenshot example here, if you look at the tag at the bottom, I specifically have a tag called cost allocation that says project X. If that was a cost allocation tag in my AWS account, I could run really cool financial reports on all of the resources that were spent supporting cost allocation tag project X. So get into the habit of tagging. It's inexcusable not to tag your stuff, in this day and age. So do it. ParallelCluster makes it super easy. All right, so that was kind of the things that you think about before. Now the sort of next content is sort of talking about, you've got a ParallelCluster environment deployed, you've got an SQL database set up. What do we have to do to get this sort of nirvana of license-aware Schrödinger job scheduling up and running? So this is where things are going to get sort of dry, and I'm going to kind of go quickly because this could easily have just been a technical blog post. I don't need to sort of monologue at you. The first thing that I highly recommend is you absolutely want to log into your ParallelCluster environment that has Schrödinger present, probably in an EFS share, and you want to run the licadmin or however you pronounce it stat command. The simple truth is if you can't query the license server and get back a happy result, none of the rest of the stuff I'm going to talk about is ever going to be functional. So your starting point whenever you talk about Schrödinger integration is as soon as you possibly can, you get on there and you start running the license checking commands. And the screenshot here shows you an example of what it should look like when it's functional. When this does not work, it's typically an easy networking security group, license server fell over, DNS is not resolving. It's not hard to fix these issues, but do not progress beyond this point unless you can get that licadmin stat command to function. Requirement number 2 is this will bite you downstream with failed jobs and users submitting support tickets. The Schrödinger suite is fantastic in that they've got this great GUI called Maestro that you can run on your laptop. Maestro knows how to submit jobs to the HPC cluster, but Maestro on your laptop needs to communicate to the HPC node. It needs to submit the job to the HPC node. It needs to move data there. It needs to talk to the node. And so this is a long-winded way of saying you absolutely need to have passwordless SSH sorted out for your users. If your Maestro users are remote, if they're on VPN, if they're in the office and you're talking to AWS, you need to make sure that passwordless SSH from the laptop or the submit device to the head node as the user running the job is going to work. And then finally, you also want passwordless SSH working for the user to all of the compute nodes in the grid. There are steps within the Schrödinger workflow where if you can't SSH without a password prompt to a compute node, it's going to die in weird ways and generate odd errors. So again, in the same way that you want licadmin stat to work, you want to make sure that for your Schrödinger users, you want to sort out and test passwordless SSH before you get too much further. It's just going to save you some heartbreak. And it's a lot easier to debug in the context here than trying to debug when you've got the cluster up and running and licenses are in play. It's just easier to sort of take this stuff and sort it out now. The final thing you want to do is, again, we're going to fail at setting up Slurm accounting unless our head node can talk to the SQL database that you stood up. The screenshot here is just showing a connection attempt to an RDS hosted MySQL instance. Nothing really special there. So that was kind of the sort of, when you've got your cluster and you've got your SQL, what are the bare minimum things you want to do to sort of, tease your eventual future success? So now we're at the point where we actually can start touching stuff. This phase is going to be starting to talk about the ParallelCluster changes we need to make. And then the final phase will sort of zero in on the minor Schrödinger configuration changes that you make to sort of stitch it all together and end up in, a nice happy place. So phase 1, Slurm configuration changes. Again, this is super dry and technical, not technical, it's actually kind of boring. So I'm not going to monologue at you at it, but the first thing that you need to do is you need to edit the Slurm configuration file, and you need to tell the configuration file that you're about to turn on accounting. And in this particular step, we're basically turning on accounting storage via slurmdbd, and we're putting in the host name of our ParallelCluster head node. The second thing we need to do is ParallelCluster right now in the 3.2 iteration does not ship with Slurm database daemon up and running or activated. Again, I have a feeling that will show up in a future release, knowing how cool they are and how fast they develop. But one of the things that I found is that even though they don't ship with a functional slurmdbd, they have a whole bunch of Slurm files cached in their chef repo. So you can actually pull the slurmdb configuration file from the path above. The path is specific to the version of Slurm, so it might be slightly different when you do this on your own. But this step here is basically saying we need a slurmdb configuration file. It needs to be an opt-slurm etc, and you can get the starting file from by stealing it out of the chef repo that the ParallelCluster people have for you. The other thing is Slurm is very picky about ownership and file permissions. So this file needs to be owned by user Slurm. It needs to be chmodded to 600 or something like that, because this is going to have like a MySQL password and other things in it. So they want it to be locked down. The next thing we want to do is we actually want to edit the contents of slurmdbd.conf. If you look at the example file, there's a ton of really cool things that you could do. I've sort of boiled it down to the bare minimum configuration that you need to have this thing work out of the box. And again, I won't read it at you. The text in red is typically the stuff that you would have to substitute in, although actually all of this, Slurm accounting database, Slurm user. But the idea here is that, there's, 7 or 8 lines, you customize it. You really just have to put in the head node host name and basically feed it the database connection information. That's really all this file stands to do. Step 4 after this is we want to set up Slurm logging log files. And Slurm tends to complain if it doesn't have file permissions or can't find the log file it's been told to write to. So this is kind of going over the top, but let's explicitly create the file. Let's touch it. Let's change the ownership. And so now we know slurmdbd is going to be able to log to where we told it was going to log in the configuration file on the previous screen. Step 5 is we need to cross our fingers, and we actually need to, oh, actually, I've got a typo in here. We are actually going to copy the slurmdbd.service file out of the chef cache. We're not taking slurmdbd.conf. We're taking, so actually the example here is correct. We're taking slurmdbd.service and we're copying it to etc systemd system slurmdbd.service. The cool thing about stealing this out of the chef repo is you actually don't have to edit the file at all. The service file is ready to go. So you copy it to the right place and then you enable it, you start it. I like to restart it just to make sure that it's going to restart without complaining. And then finally you run the status command. And what you want to do at this step is you want to make sure that the slurmdbd daemon is up and running. It's not complaining. It's basically sort of happy. One of the things that you will find if you have a parallel cluster that mixes and matches dynamic nodes with static nodes, the static nodes in your cluster that are already present and sort of hanging around in your grid, they know when you're messing with Slurm configuration files, and they will know when they've been dealing with a Slurm configuration file that is now out of date relative to the edits that you just placed. So this is just kind of a gotcha page here. If you see an error like this, don't panic. It just means you have to log into your persistent compute nodes and tell them to reread their configuration files. Then the errors go away. And you don't have to worry about this for dynamic nodes that scale in when they're needed, because when a dynamic node scales in, it's always going to read the latest version of the configuration file. But if you have static nodes, you're going to see errors like this in slurmctld.log. Finally, and this is the important step, this is where we actually tell Slurm to create some database stuff and start treating the SQL server as a remote data store for our accounting information. The most important thing here is these commands need to be run as the Slurm user. So you can follow these commands, become Slurm, run a couple of Slurm accounting manager commands, and then finally, this is the last step, is a Schrödinger specific thing. It's good to have a .Schrödinger directory in the Slurm, wherever your home folder is for Slurm. So these commands can just be followed as is. So finally, sort of recapping where we're at in phase 1, we haven't touched Schrödinger yet, but if successful, we've basically taken the stock parallel cluster environment, which ships without accounting enabled, and we've completely set up Slurm accounting, which is actually really cool for a lot of use cases way beyond license aware job scheduling. There's very valid reasons to have accounting set up because A, it's very useful information for your end users. So this is great. If you've got to this point, you've successfully configured ParallelCluster to be far more useful to your sort of human researchers and human scientists. And we've integrated an external SQL database into the mix. So now we're ready to teach Slurm about the existence of licenses, and we're ready to teach Slurm about FlexLM. So that's going to go in this next set of slides. So now we're in phase 2, where we've stepped away from the parallel cluster config changes, and now we're talking about Schrödinger configuration changes. The first thing we want to do, and this is again, thanks to the developers at Schrödinger, is Schrödinger makes this really easy. If you go into the utility subdirectory of your Schrödinger root, there is going to be a Python script that is called slurm license sensor. This is the heart of license-aware job scheduling, and I'll talk over what it's going to do. Basically, the Slurm scheduler needs to be aware of licensing because it needs to hold a job in pending state until a license is available. Because if you send a job out for execution and a license isn't available, the job is going to die, and your user is going to be unhappy, and they're going to have to repeat a bunch of work. So if you want to understand where the rubber meets the road, how this sausage is actually made, the Slurm license sensor script is the magic sauce. The Slurm license sensor script is a Python script that talks to the FlexLM server, dumps the current license state and status information, and then reformats that information into a way that the Slurm accounting database can consume. So the bridge between Schrödinger licenses and Slurm HPC scheduler is this Python script. It's literally that simple. And so I'm going to talk through the steps you need to do to sort of get this Python script up and running. So the first thing you need to do is you need to make it executable. It's not by default. The second thing you should do is own it, is change the ownership to Slurm, because we're going to be running it as the Slurm user when we run it regularly. And then finally, if you try to run it as is, it's going to fail out of the box because it's looking at a different path for the Slurm binaries than where ParallelCluster actually installs the Slurm binaries. So you're going to have to edit this file no matter what. Fortunately, the edits are trivial. They're documented right here. So the first thing you need to do is you need to change slurm install dir to opslurm. That's the base path in ParallelCluster where the Slurm binaries live. And then finally, you need to name the clusters that are going to be in the mix. ParallelCluster, if you look at slurm.conf, the name of the cluster is ParallelCluster. So unless you've changed that for some reason, you're going to make these exact settings in the Slurm license script, and that's all you need to do, and you're good to go. What you do after you make these changes is you try to run it. And like, if I had to stop the webinar at any point, like, this is like a good stopping point. Like, at this point, we've just told the Slurm HPC scheduler all about our Schrödinger licenses and all of our Schrödinger features, including what feature, what entitlement, and actually how many licenses are available for each. So like, just getting to this point is like a cause for celebration. So this is the output that you see when you're running the Slurm license sensor script sort of interactively. I'm going to stop talking about Slurm license sensors running at 30 seconds, and I'll just sort of keep going here. So the final thing we need to do is, if you want a systemd service to run every 30 seconds, basically, I'm going to go back. You want the service file, and then you want the timer file. So again, without emoting or monologuing at you, this is all you really need to do to set up a systemd service that runs regularly every 30 seconds. If you do it right, again, we want to fix the log files. So again, we want the Slurm license server to log properly. So we do a little bit of file permissions and file ownership permissions just to make sure that logging is happy. And then finally, we start the service, via standard systemd system control things. But again, this is an issue where this is really important. If this script doesn't work, Slurm is not going to be constantly aware of our licensing situation. So you want to test by verify. There's a couple of different log files that you can look at. But again, if we look at syslog, we can see, clear signs that this is kicking off and running every 30 seconds. And we can always run scontrol show like, on the Slurm side to confirm that it still has a proper view of licensing and things like that. So that was the end of kind of the license, the load sensor. To be honest, that's probably the most valuable and possibly the trickiest part to get up and running. If you get here, everything else is cake. The final sort of, among the final Slurm configuration things that we want to do is, by default, Schrödinger knows how to submit to Slurm clusters. But by default, it does not behave in a license-aware way because the Schrödinger people know that not every Slurm cluster is license-aware. So what's going to happen is you're going to go into the Q subdirectory. You're going to find, I don't know why they call their Slurm integration Slurm 2.1, but you're going to have to go into Slurm 2.1 subdirectory and you're going to edit the configuration file. You're going to make just 3 changes. The changes are in the screenshot here. They're highlighted in the bold black text. You want to change the Q path so that it knows where to find the Slurm binaries, and then finally, the most important bits are down at the bottom. By default, license checking is disabled, and by default, remote license server is not configured. So one of the final major steps we're doing here with Schrödinger is we're going to go into their Q configuration directory, and we're actually going to enable the features that will change the Schrödinger job control system to the point where I guess this is a long-winded way of saying this is when you have license checking and equals true, then Schrödinger job control is going to submit jobs to Slurm that actually make license requests. You'll see the -L, license feature, number of license features needed. And so this, just like the load sensor, this is the sort of magic glue that makes it all happen. We want to slightly edit this configuration file. We want to turn on license aware behavior. If you do that, the Schrödinger job control system basically handles all the messy work for you. Finally, we're kind of getting near the end here. We're kind of getting near the last of the phases here. It's actually time to mess with Schrödinger.hosts. And I want to talk a little bit about Schrödinger hosts. In the same way that I mentioned that the load sensor script is the heart of the integration, the Schrödinger host file is the heart of your user-facing environment and the heart of your user-facing experience. Everything related to Schrödinger reads this file to understand how to submit work to remote resources. So everything that you do here, and this is where you can completely control your environment. You can override Slurm arguments. You can pass environment variables. This is where you would do that JProxy, JServer stuff if InfoSec wanted to control the port ranges being used by the job control framework. Schrödinger host is kind of where you define and write down exactly how Schrödinger is going to submit jobs to your HPC environment. What queue, what partition, what arguments is it going to pass, what environment variables are going to be set in the job context. This can be a fairly complicated file. In my pharmaceutical and biotech customers, we might have 10, 12, 13, or 14 different Schrödinger host entries ranging from big standalone large memory nodes to that NVIDIA DGX cluster with all of the GPUs in it to HPC environments. So it's normal that this file is in constant flux. It's normal that this file is complicated. The only hassle I want to tell you is that if you have laptop users who are working at home or on VPN or remotely, basically not connected to your shared storage, you've got to work out a method for getting the Schrödinger host file to them and communicating changes to the Schrödinger host file to them. Because at the end of the day, a scientist, she's sitting with Maestro at her laptop working from home. She needs a local copy of Schrödinger host in her environment so that she can use the Maestro GUI to send the job to the right HPC cluster with the right arguments and the right settings. So I think the only annoying thing about Schrödinger host is that this is not only a file that you're going to have to maintain, this is a file where you're going to actually have to operationalize how you disseminate changes, particularly to people who have Schrödinger locally installed on their laptop. This is the simplest possible Schrödinger.host entry. The Schrödinger documentation is fantastic. There's a lot of, at developer guide and admin guide information on this, but just to kind of step through here, this is what would allow you to have a Maestro user send work to a target called pcluster CPU queue. And so we name it in kind of a human-friendly way that sort of delineates maybe the resource where it lives. And in particular, we want the name of the resource to be highly specific. This is a CPU queue. There aren't going to be any GPUs in this queue. Don't send GPU jobs to this environment. The host is an IP address. You can see here Slurm 2.1. If you remember a few minutes ago, we were editing files down in Slurm 2.1 to turn on license-aware behavior. And then finally, you can see the QArgs department. This is where we explicitly route jobs to the CPU queue partition, and we pass a few other things, particularly for threaded or SMP jobs. We want to make sure if it's a 4-processor job, Slurm will allocate 4 processors for that job and not just try to pin it all on one. Again, we set temp tier, and then again, we explicitly set the Schrödinger path. And again, you can see here, I'm using Schrödinger and then a subdirectory that's specific to the base name. So it's okay to have multiple entries. It's going to be common to have multiple Schrödinger host entries. I often will have a individual Schrödinger host entry for every queue or every partition in my HPC environment, so that you don't have to solve this with a one-size-fits-all solution. So this is the CPU queue example. This is a little bit more complicated environment or setting, just kind of showing you, this is my sort of default starting point when I'm sending jobs to GPU queues. We're passing in some grez, I don't know how Slurm pronounces it, grez, I'll say, but there's some particular things related to requesting GPUs, requesting resources. And then finally, down at the end of that entry, you can see here, for this particular queue, we're using instance types that have a single v100, and because it has a single v100, it's at PCI device ID 0. So again, we're telling it, use the v100 at device 0. And then finally, we're setting some environment paths. Don't blindly copy this configuration file, because for instance, if you see CUDA cache path, we're referencing a directory called scratch CUDA. If scratch CUDA doesn't exist in your HPC, stuff's going to break. So, this is kind of reference material. You might have to tune it or tweak it a little bit. The other thing I wanted to talk about here is, and I'll go back to a previous slide here. If you notice in the host line, I have a bare IP address. There is a very specific reason for that. The very specific reason for that is we have job submitters, we have Maestro users who are external. They're not necessarily going to be able to resolve Amazon AWS host names. So for instance, in our prior Slurm configurations, we were doing things like IP, number. That type of host name is probably not going to resolve to someone who's working from home. So it is totally cool. It is totally fine to drop bare IP addresses into Schrödinger host. If you want to be fancy, you can have a DNS entry and substitute a fully qualified domain name. But the key thing here is you don't want to make Schrödinger host entries where you reference a host using a name that is not resolvable universally. So it needs to either be a bare IP address or it needs to be a host name that will resolve wherever you happen to have Maestro job submitting users sitting, working, or co-working. All right, phase 4. This is basically, we're done. And I can see this was kind of fairly boring and sort of dry. There's a lot of steps, but not all of the steps are not particularly difficult and they're not particularly problematic or troublesome. So if we've gotten to this point and we haven't gotten any crazy errors, it's time to test. And again, I'm a big believer. I've done a lot of HPC troubleshooting. Whenever you want to test, you want to simplify the solution space as much as possible. So absolutely, test number 1 that you do is you throw Slurm out the window and you confirm on the command line that you can run a Schrödinger job that pulls a license server and it runs successfully. So this example here, command line using the run like test, basically it's running in debug mode so you can get some good output. It's going to pull 4 lib licenses and it's going to hang for 100 seconds and then it's going to exit. So this is a really good test of your Schrödinger configuration, your networking, your security groups, and communication with the license server. If this doesn't work, the Slurm stuff's not going to work. So again, this is kind of another good sort of baseline configuration test to do. It's actually also kind of cool to pull licenses from the command line and verify that license sensors and things like that are working. The cool thing is that even though we ran this job outside of Slurm, we still consumed licenses. And we still have a license server that's reporting license counts into Slurm. So if you're quick and you have 2 terminal windows open and you're checking the contents of SCHRODINGER show like, and you're checking the contents of the Slurm license server, you can actually see the state transition for that test job that we just ran. You can see that there were 1047, and for a short time there were only 1043 because we were consuming 4 of the libs license entitlement features. So this is also a good sign that your load sensor is working. If you consume licenses outside of Slurm and you monitor Slurm to see that Slurm picks up the state change in the number of entitlements that are available, just seeing it go to 1043 from 1047 is a sign that things are generally working under the hood. Finally, this is probably the last test, and this might be actually sort of the end of my prepared material. So for those of you in the chat or those of you who have questions, start queuing them up, or I'm definitely going to end before the top of the hour. Schrödinger also has a really fantastic and fairly comprehensive script that they call the installation check. The cool thing about the installation check script is that you can pass arguments that will match against entry in Schrödinger host. So in the example, I showed you I made a Schrödinger host entry for pcluster CPU queue. I can actually run the installation check, and if I pass the -test argument and I give it the name of something that I've defined in Schrödinger.hosts, it's actually going to use that remote compute environment to run its installation check. So this is the best overall test because the end result of running this script will be a Slurm job, or it will be an attempt to submit a Slurm job. And this is kind of where the rubber meets the road. If you can pass the installation check, then basically you're done. You have license-aware job scheduling. You could be fairly confident that a scientist doing real work with Maestro, command line or GUI is going to be able to successfully submit license-aware jobs to the cluster. So again, installation check is your friend. I love it. I run it all the time. It's the first thing I do when I'm troubleshooting a Schrödinger environment. And let's look at some of the output here. The output is fairly verbose because it is designed to be an installation check. But what you can see here is it's reporting success. The interesting thing is JobControl has its own concept of job IDs. And job IDs in Schrödinger JobControl are totally different from Slurm job IDs. But there is a way to unify them. There is a way to sort of correlate between them. What you're seeing here is the installation check reporting that it was able to successfully use the pcluster CPU queue target in Schrödinger.hosts. And more particularly, because JobControl knows how to talk to Slurm, this is showing you that it successfully submitted a job to Slurm, it successfully monitored the execution of that job, and it successfully confirmed that the job exited cleanly without errors. So this is kind of the holy grail. Like, I wouldn't necessarily call this an acceptance test, but this is some of the things that you would be doing, under the loose category of, is crap working, or, is this stuff going to work when I hand it over to my scientists? And then finally, again, I'm a big fan of trust but verify. In this previous slide, I'm showing you Schrödinger output. Every time I see Schrödinger telling me something, I want to ask Slurm the same thing and see if they agree. So this is Schrödinger's view of what the job and the job ID looks like. But if I'm careful and I catch it at the right time, I can use Slurm commands. And you can see here, SQ command, this is literally the first job I ran on the new HPC cluster. So it got job ID run, it's running in CPU queue where we expect it. The name and paratest is what we expect. And then finally, we could dump a bunch of verbose information, SCHRODINGER show job, job ID, we'll dump a whole bunch of information. And really, like, this might look boring and dull, but the key thing to understand here is Schrödinger submitted this job to the queue. This was not an S-batch or an S-run command that I did or a chemist had to done. This is the Schrödinger Maestro GUI programmatically understanding how to move work to an HPC environment, format it into a batch script, and then submit it to the Slurm cluster, also with the accompanying license request arguments that will hold the job in pending state until a license is free, at which point Slurm takes over and runs the job, when its awareness of license matches what the job is requesting. So as boring and as dry as this is kind of like the nirvana or aha moment. You're at the point where Schrödinger Maestro has submitted a Slurm job automatically, autonomously through SSH with no user or chemist or structural biologist, having to do anything funky down on the command line. So finally, I think I generally just sort of talked over this. I think this is probably fairly close to the last slide, if not the last slide. But to recap, we have Schrödinger installed in an EFS share. We've got it mounted to our ParallelCluster environment with a healthy license server that we can talk to. We went through the steps. I didn't show you how to stand up an SQL database, but I showed you how to create the database within it. And then we showed you how to create the slurmdbd and configure the slurmdbd service, which is a prerequisite for turning on accounting. We activated accounting within Slurm. And I really should have included this in material here. Like, there's a lot of value to having Slurm accounting functional out of the box that is independent of having license aware job scheduling work. So your users are going to thank you, even if you don't do the license aware stuff. Just having accounting is useful. The third thing we did is we set up the 30-second license sensor. And again, I think because my audio was sketchy when I was talking about that, I do want to recognize that, polling a FlexLM server and updating Slurm every 30 seconds is not perfect. There's obviously a race condition where within that 30-second window, if someone steals a license on another host, you could end up with jobs dying because there's a slight race condition or mismatch. This is the closest that we're going to get. All of the sort of license-aware job scheduling schemes that I've seen, they don't integrate at an API level. They all use this concept of a floating polling server. And eventually, either your users aren't going to notice the race condition, or if the race condition does become problematic, it's a relatively simple fact to submit your jobs as rerunnable. So if they fail for a transient license not found error, Slurm can requeue them and rerun them automatically. And generally, Maestro and the end user aren't going to know that there was a temporary license glitch. Moving on, we had to customize the Slurm queue configuration to turn on license-aware job scheduling. We needed to override the path for where Schrödinger would look to find Slurm binaries. And then finally, we ran on the command line a Schrödinger command that checked out a license and paused for 100 seconds. We verified that even though we were running outside of Slurm, the HPC cluster still picked up and detected the change in license count. And then finally, we used the Schrödinger installation test script to directly target the entries that we put in Schrödinger hosts, including directly submitting jobs to the Slurm scheduler with the appropriate license-aware job requests. So that's it. I can't believe I actually finished a few minutes before the end of the hour. Normally I'm super verbose and I run over time, but
cool. So, okay, we did get a few questions. Just see if we can kind of plow through these. So I think we're just looking at Darren's question about using Schrödinger licensing on demand and figuring out the optimal number of licenses you need.
Yeah, so I'm unfamiliar with licensing on demand. I'm used to sort of dealing with fixed entitlements in a Schrödinger license file, but I do want to talk about the other related part of that question is that it is incredibly important and probably worth another webinar or technical blog post on what to do with your licensing information. These are not cheap software assets. You want to be able to report on what percentage of them were in utilization. You probably want to be able to report to management the number of hours that a chemist had to wait for a license and things like that. So this is outside of the scope of ParallelCluster or even Schrödinger, but it falls into the scheme of sort of FlexLM license monitoring and reporting. What I've found is that if you enable debug or verbose logging on the FlexLM server, there's a couple of open source and several commercial products out there that will ingest your FlexLM logs, and they will provide really cool time-based reporting on how efficient and how effective the utilization of your expensive software assets were. I've got 2 pharmaceutical customers where we're doing this now with really sort of a lightweight free PHP script. But when I was looking at solutions in this space, there were a number of commercial products in there as well. People who are trying to sell you services to maximize your, the amount of money you're spending on commercial licensing. So yeah, if there's interest in this might be worth another talk. I didn't really talk about what we do with the FlexLM license data over time. And there's some interesting stuff happening in that space.
Excellent. Okay, how easy is it to adapt this approach to other FlexLM-based applications?
To be honest with you, I think it would be very, very easy. In fact, if you are not a Schrödinger user, what we might be able to do is, if you can get that load sensor script, but basically at the end of the day, you don't even need that Schrödinger load sensor script. If you can run the command licadmin stat and format the output and then emit SCHRODINGER license commands, that's basically all the load sensor script is doing. So if you have a general interest in making ParallelCluster aware of FlexLM licensing, then there's 2 things that you need to solve. You need to pull the FlexLM license server and insert the correct numerical values and license names into Slurm. And then the second thing you need to do is you need to teach your users or your workflow how to pass the additional, I think in Slurm it's -L. -L is a license request. If you could do those 2 things, you could basically integrate any FlexLM aware application into Slurm. The only 2 components required are teaching Slurm about what licenses are available, and then finally teaching your users how to make a license request on the command line, which is really just a -L argument to B sub S run, whatever job scheduler you're using.
Got it. So, and the last question is, do you usually use the same EFS for Schrödinger and other applications, or dedicated EFS?
That's actually a really good question. I'm actually a fan of using the same system because I like having all of my scientific tools installed in a universal environment that I can mount on any Linux system in my plant. So that means I've got 8 different versions of R. I've got all my Python condas, everything else all in one share. There could be arguments maybe for cost control, or if you wanted to isolate the systems for doing individual EFS. The only other thing I've sometimes done individual EFS is when I'm on, Graviton architectures or something like that, where I'm worried about code compatibility. But even then, a sensible organization of your EFS share into, architecture-specific binaries, you can get away with one. So I would say I'm a fan of one. I find it's broadly useful to sort of have all of my scientific software installed in one EFS mount that I can easily present to ECS, to ParallelCluster, to EC2 server, but you don't have to do it that way. And from a cost and implementation perspective, it's not hugely different to carve out your own EFS share if you just wanted to put Schrödinger on there. And I know some Schrödinger users, because they deal with super sensitive chemical and compound data, there might be an argument for isolating this on a separate EFS share if you don't want to, potentially expose anything related to what you're using the Schrödinger platform for. Although I don't think any of that data actually lands on the EFS system. That's typically on the laptop of the Maestro user. That's where the sensitive data lives.
And I guess kind of a similar question. So do you have all of your applications on an EFS share, and is EFS fast enough for that?
Yeah, so EFS is generally fast enough that I use the default configuration of EFS. In the early days, EFS used to get bigger the more you put into it. I think the under the hood enhancements, that's not really the case here. EFS is kind of broadly, generically fast enough. Basically, my default stance with EFS is I start with EFS and I only go to something like FSX Luster or even something commercial like a Weka file system. Our starting point is EFS, and we only move to a more performant solution if business, scientific, and budgetary reasons allow. So I would put all of my applications in EFS. Where you run into EFS speed issues is sometimes down at the data level. Outside of the chemistry stuff we've been talking about with Schrödinger, there's some machine learning stuff, there's some bioinformatics stuff, there's some genomic stuff where either you're dealing with very long sequential reads against big files, or worst case, you have subdirectories with tens of thousands of tiny files. There's going to be EFS use cases where EFS is going to feel slow to your application. But from a Schrödinger perspective, for this webinar, EFS is more than fast enough to load the Schrödinger binaries and anything else that we care about.
Excellent. Well, thanks everyone for hanging out with us today. And yeah, sorry again for the technical difficulties. Also, huge thanks to Chris for making this work despite being at a conference on guest Wi-Fi. So we appreciate you. And yeah, and so the video will be sent to your registered email address on Friday. Look for future upcoming webinars. And yeah, I don't know, Chris, any final words?
Nope. Hope I turned on my camera. I bet the bandwidth is good just as we end. So thank you, everybody. Yeah. Thanks, everybody who stuck around to the end. We really appreciate it.
All right. Thanks, everyone. See you next time.
Yep. Bye-bye.